Okay, we are ready, sir.
Just give me one moment. Huh?
Yeah.
I'm in total darkness today.
Right.
Yeah. Okay, one moment. Let me see if I can do that. Okay, anyway, we'll have to do with it. All right, good morning. So I'm going to continue with my lecture on white dwarfs. So I'm hoping that you're not finding them too difficult, because there's a lot of physics here rather than the astrophysics. Okay, one moment. So we'll start again with, I'll very quickly recapitulate the most important things that we did yesterday. One is that the Maxwell-Boltzmann distribution, which applies to classical gas. So when you got a gas with a certain number density of particles, and then you got a temperature T, then you know this is the Maxwell-Boltzmann distribution. And here you can see the distributions plotted for different values of the temperature. And as the temperature increases, the distribution gets broadened, as you can see here. Now, the point is that in a classical gas, it doesn't matter how high the density is, but in quantum mechanics, you know that you have the Pauli exclusion principle. So, which means that in a given state, that is in a given volume of phase space, you cannot have more than 2 electrons, which I described to you at length yesterday. So, so what happens here is that we look at the volume of phase space with a small space volume element dV, and the momentum volume element is between there's a sphere of radius p, and so you're looking at the the number of phase space elements between p and p plus dp, which is 4 pi p square, which is the area of the sphere, times dp, which gives you the volume, and this is the volume in configuration space. So then you have got to divide that by h cube to get the number of quantum cells. So per each electron, for each quantum cell, then we can have 2 electrons. That is because the electrons have spin up and spin down. Right? So now Pauli's exclusion principle requires that in this volume, the total number of electrons in Fp dp dv must be less than or equal to 8 pi p square by h cube dp dv. So, so here you have got your Maxwell-Boltzmann distributions, and this is the Fp is equal to p square curve. And then you will find that when the temperature is high and the density is low, Pauli's exclusion principle is not violated. But as the temperature decreases, because you see, what do you mean by temperature? What happens when the temperature decreases? The momenta are all much smaller. And therefore, all the electrons tend to get packed in the lower momentum states. And when that happens, then you exceed, then you start violating Pauli's exclusion principle. So then you say that, all right, I should not be considering the classical distribution at all, and I must invent a new distribution. And that distribution is the Fermi-Dirac distribution. So, but let us consider the distribution for the limiting case of T is equal to 0. Now, this would not be permitted in classical physics because you cannot reach absolute zero there. But in quantum mechanics, there's no problem with that. So you consider T is equal to 0. Now you say that there are these electrons, which classically would all have 0 energy, but here they must fill the momentum states because you can't have all the electrons in the state P is equal to 0. So when you start filling the states, what happens is that you say that I put 2 electrons in one cell, then 2 electrons in the next cell, and so on and so forth. And you go on doing that until you have exhausted all the electrons. What do you mean by all the electrons? If you are doing it by unit volume, the number of electrons by definition is Ne. Right? So we are packing in the electrons here. And when you do that, then you go up to a maximum momentum, which is known as the Fermi momentum. Right, so this is at a gas like this, which is at T is equal to 0, a quantum mechanical gas is known as a fully degenerate gas. So here we have got a fully degenerate gas with gas with T is equal to 0, and so the distribution function is Fp is equal to 8 pi p square by h cube, when p is less than the Fermi momentum and is equal to 0. There are no electrons outside that. And that gave us the particle number density in terms of the parameter x, which is the relativity parameter, which is Pf by MEC. And so you must understand that Pf is not given to you. You don't know what the Fermi momentum. You know the Fermi momentum only when you have got the density. Because you look at the density, divided by these constants, you get the value of x, you put that in here, and you get the Fermi momentum. So clearly, higher the density, the greater is the Fermi momentum. Right? And this is the expression for density. And then the expression for PE, which is the pressure due to the electrons, as I told you, is the constants here times the function fx. So this x and this x are the same. So you see that I have got, if you give me a value of n, I can find the value of x and then put that in x here. Then I know this function, I know the pressure. So given the density, I know the pressure, and that means that I got the equation of state. Right? So, and what are the equations of state we apply? We consider two cases. One when x is much less than 1. Sorry. Come on. One when x is much less than 1, which is a non-relativistic case, in which case the equation of state was the pressure of the electrons is rho 5 by 3. And then in the relativistic case, it was the pressure of the electrons is rho 4 by 3. The pressure equation of this form, that P is equal to K rho to the gamma, where both K and gamma are constant, is known as a polytropic equation of state. Right? So what we have shown is that the equation of state of a fully degenerate gas takes on this very simple form, and you make a transition from 5 by 3 to an index of 4 by 3 when you go from the non-relativistic case to the extreme relativistic case. All right, so we stopped here the last time, and what I want to do now is now see what is the implication of this. Now, if you remember, yesterday I told you what is the equation of hydrostatic equilibrium, and that was that dP by dr is equal to minus gmm rho by r square. And then I showed you a particular relation which comes from it, which is an approximate form, and which is P by m, where P is the pressure, goes as gm by r to the 4. So m is the mass, r is the radius, P is the pressure. Right? Now, what is the equation of state that we have got here for a polytrop? That P goes as rho to the gamma. Now, the density rho is approximately m by r cube. I am ignoring numerical factors. And so P goes as m by r cube to the gamma. Now, consider the quantity Fp, which is equal to P by m, and that goes as m to the gamma minus 1 upon r to the 3 gamma. Then we have got a quantity which is called we have got a quantity which is called now I'm calling it Fg, and that is equal to m by r to the 4. Now, now consider F, which is equal to Fg by Fp. And what is that? It's a simple expression, m raised to 2 minus gamma for r into 3 gamma minus 4. Right? And so now we have got two values of gamma, you remember. Gamma is equal to 5 by 3, which is non-relativistic, and gamma is equal to 4 by 3, which is relativistic. So what is the so what do we get here? So F goes as m to the 1 by 3 r in the non-relativistic case, and F goes as m to the 2 by 3 in the relativistic case. Now, what is F? So let us go back here. So Fp is simply the left-hand side of this equation. Fg is the right-hand side of this equation. apart from the constant. And therefore, so what is the now what is the condition for equilibrium, hydrostatic equilibrium? That P by F, which is Fp, is equal to Gm by R to the 4, which is Fg. Right? So which means that for equilibrium, you have F is equal to 1. Right? So now, so what are these objects? These are objects which are fully degenerate. These objects are fully degenerate with a mass m and radius r. So now let us come to the non-relativistic case. So what is the condition for hydrostatic equilibrium? That is F is equal to 1. So which means that m to the 1 by 3, F is equal to 1. So which means m to the 1 by 3 is equal to 1. Which should mean that R goes as m to the minus 1 by 3. Right? So, so now you must pay careful attention to what we have here, because I have taken very simple arguments here and arrived at the very important conclusion that if you have got a fully degenerate object, then the radius of that object must go as m to the minus 1 by 3. Now you may recall the last time what I did was that I showed you a graph in which I had plotted R against M, and I had shown that for normal stars, meaning what are normal stars? The stars on the main sequence, R is roughly proportional to M. So you had got as M increases, R increases. But it is an observational fact that for white dwarfs, as the mass increases, then the radius increases. So here we have got a representation of that, because we are going to represent a white dwarf by a gas of fully degenerate particles. Why do we do that? Because we already recognized that the mass of a white dwarf being what it is, comparable to the solar mass, and the density being 100 times less than the density of the sun, then what happens is that the radius being 100 times less than the radius of the sun, the density is 1,000,000 times more. And we have shown that when the density is so high, then quantum effects are completely unavoidable. And therefore, we have to consider a degenerate gas. And for that, what is the important conclusion? That R goes as m to the minus 1 by 3. Now, let us consider the consequences of this particular condition. Supposing I take a whole series of white dwarfs, right? I take a whole series of white dwarfs, and then I arrange them in a sequence so that on the left of the sequence, I got the lowest mass, and as I go towards the right of the sequence, I get higher and higher masses. Then what happens to the radius? As I go to the right of the sequence, the mass increases, and therefore the radius decreases. And as the radius decreases, the density increases. Right? So the interesting thing then is that I go to higher mass white dwarfs, and then I get increasing density. But we have seen here that as the density increases, the thing will become, the x will increase. And so therefore, you can imagine a situation where x becomes much larger than 1. And when that happens, and then the electrons in the white dwarf become relativistic. And when they are relativistic, what is the relation? The relation is that F goes as m to the 2 by 3. So you see now, look at the profound difference between this M when the gas is relativistic and here when the gas is non-relativistic. Here the object has got the condition for equilibrium has 2 parameters in it. So if you give me the masses, then I only have to adjust my R in such a way that the greater the mass, the lower is the radius, and it follows this law. Then I will get an equilibrium configuration, no matter how high the mass is. But there is an upper limit to the mass, because as I increase the mass, I will eventually reach a point at which the density is so high, and that is about 1 ton per centimeter cube. When the density becomes as high as that, then the matter becomes relativistic. The electrons become relativistic, in which case I have to leave this relation and come to this relation. But here there is no R. So which means that if I put F is equal to 1, then I get an absolutely unique mass. Right? So to understand this important conclusion is that when the degenerate object has relativistic electrons, then there is a unique mass for which hydrostatic equilibrium is possible. And that unique mass is the Chandrasekhar mass, and it is this particular value that you see here. Now, how do I get this value? There is a rigorous way of doing it, but I will now show you a very beautiful intuitive argument which leads to this Chandrasekhar mass. Right? So now let us look at this argument here. Now, from the uncertainty principle, you remember that we are in the quantum domain, and therefore the uncertainty principle is applicable. You see that we have already applied the Pauli exclusion principle, right? Because we said that it is because of the Pauli exclusion principle that we have this concept of a Fermi momentum. Otherwise, we wouldn't have had that concept. So now we are introducing the second concept, which is the uncertainty principle. And what is the uncertainty principle, Heisenberg? It is delta x into delta p is equal to h cross, right? So now for delta x, what is delta x? You can see that delta x is the interparticle distance, the average distance between the electrons. And you may remember that yesterday I explained to you at length how the interparticle distance goes as n to the minus 1 by 3. So delta x is n to the minus 1 by 3. Now I need an illustrative value for the uncertainty in the momentum. So I'm just making the approximation that delta p is equal to pf. What is pf? Pf is a characteristic momentum, right? Which is the Fermi momentum. And because we know that the electrons are relativistic, okay, so therefore everything will be all the momentum will be higher than momentum. So this is a lower limit that we are taking. So uncertainty principle now translates to n to the minus 1 by 3 into pf goes as h cross. Right, so therefore pf goes as h cross into n to the 1 by 3. And what is n? N is the number of particles per unit volume, and that is equal to the total number of particles in the object divided by r cube. As usual, I am neglecting the factor 4 pi by 3, right? So n by r cube raised to 1 by 3. So h cross is equal to m by r cube. What is n? N is the total number of particles. So that will be equal to the mass m times divided by the average mass per particle. So if I assume for simplicity that it's all protons, then I'll get mp here. So I get pf goes as h cross m to the 1 by 3 r upon mp to the 1 by 3. But now, what is pf? What is the expression for pressure? The pressure is the amount of momentum which is the amount of momentum which is conveyed per unit area per unit time. And so, and from your elementary physics, you know that we can write the pressure roughly as the particle number density times the average velocity of the particles into pf. So now what is our average velocity? Because we are considering a highly relativistic gas, so we can take V is approximately equal to C. So the pressure is equal to NCPF. So pressure is equal to capital, and then the total number of particles by R cube into PFC, and that is equal to, again as before, M by MP R cube into PF. We have got the value of PF here, which is h cross m to the 1 by 3 upon R into MP raised to 1 by 3 into C. And that comes to m to the 4 by 3 h cross C upon R4 MP to the 4 by 3. So you see that we are slowly moving towards the kind of the combination of fundamental constants which occurs in the Chandrasekhar mass. So now we have our famous FP, which is the left-hand side of the equation for hydrostatic equilibrium, and Fp is equal to P by M. And we know that as Fp is equal to P by M, so if you go back to the previous slide, we have the value of P here. So Fp is equal to this particular quantity. And therefore, now the condition for equilibrium is Fp is approximately equal to Fg, which translates to this particular expression goes as Gm by R to the 4, which implies that m to the 2 by 3 is given by the right-hand side here, and therefore m is equal to h cross c upon g np square. There is a 3 by 2 np. And then if I plug in the constants, then you'll get this equal to approximately 2 solar masses. And what is this? This value is therefore the Chandrasekhar mass. So what is the significance of the Chandrasekhar mass then? You see, when I have a non-relativistic gas, then it is possible for me to have R goes as m to the minus 1 by 3. So given the mass, I can adjust the radius to get an equilibrium configuration. But as mass increases, then I have to take into account the fact that the gas becomes relativistic, in which case this relation is no longer holds, and I get F is equal to m to the 2 by 3. So there is a unique mass. And what we have done is that we have used the arguments of quantum mechanics to say what is that unique mass equal to. So, so I hope I convinced you that the very simple physics which I introduced, and the polytropic equation of state, which applies to applies to the fully regenerated gas, leads to the very moment, the extremely important conclusion that white dwarfs have a mass which is a maximum mass and which is equal to the Chandrasekhar mass. And why is this such a revolutionary conclusion? And that is because you can ask yourself the question, what happens if the mass is exceeded? I mean, do we say that there is a cosmic conspiracy by the result of it? No white dwarf will ever have this mass exceeding M Chandrasekhar? That is not clear. Because you see that the mass of our sun is MC is equal to 1 solar mass. We can easily have stars of 40 solar masses and 60 solar masses. And we have already seen very briefly that when these stars, they finish their, when they finish, they exhaust the hydrogen, then they go into a situation of helium burning and so on and so forth. And then when you go up to iron, there's a collapse. Now the mass of the collapsing object, depends upon, because there are two parts to the object. One is the interior part of the star which collapses, and then there is the outer part which is blown away either as a planetary nebula or as a supernova. Now the mass of the collapsing part, that is what determines the physics of it. If that mass exceeds the Chandrasekhar limit, then there is no equilibrium, which means that it must go on and on and on collapsing. So what happens then? Now, I'm sure that you have heard that when Subramaniam Chandrasekhar did the calculation for the first time, came to the maximum mass limit, he was only 21 years old. He published the paper in 1931. He did the calculation about a year before that, I believe, when he was on this ship to take him from India to Cambridge. And then, when he did this calculation, he did not know what comes after that. Okay, he just left it. I mean, he said it happens and he just left it there. So now we know that when there's no equilibrium possible, either you get, for a white dwarf, either you get a neutron star associated with a supernova, or you get associated with a supernova, okay, or you get a black hole. I'm sorry because of noise disturbance. Just one moment, please. So, so you get a black hole. So all of that astrophysics comes out of this this very simple uh, conclusion that we have come to. So this particular derivation of the maximum mass, I believe, is due to Landau. I'm sure you have heard of Landau from the books Landau and Lifshitz. So the very great Russian astrophysicist, Soviet astrophysicist, and this is his work. Okay, now see, there's a fair amount of hand waving in our calculations, where we considered x much less than 1, where we got p goes as rho to the pi by 3, and then we considered x much greater than 1, and then we got p goes as rho to the 4 by 3. Now the point is that clearly, in reality, you cannot just work with these extreme approximations. What you need to do is to work with the correct value of x, the exact value of x. And what Chandrasekhar did was that he went on doing these calculations and published a series of papers after his first paper in 1931. And in 1935, he published a paper in which he worked out the solution for a full value of fx. I have not told you what that function is, but he did it for that fx. And then what he got was this particular result. So you see that if you ignore the fact that you are going into relativity, then you see m goes as r to the minus r goes m goes as r goes as m to the minus 1 by 3, and for that you get this particular curve. Okay, which you see here, the blue curve. But you know that at some point it becomes relativistic, and then here in Chandrasekhar's theory, that can be very well worked out. So you see that you've got the solution here, and for small values of the mass, which correspond to small values of x, then it agrees with this approximation. And then when you come further, then you see that it suddenly starts going down, and then it hits the limit here. And this is the point at which this is the maximum mass. And that maximum mass can be rigorously calculated to be about 1.4 solar masses. And so, so this is the Chandrasekhar theory. And what I should do, I'm sorry, I've flipped a slide there. So what I should do, what I should say here is that this table is from Chandrasekhar's 1935 paper. And so you've got the mass here, and then you've got the density, and then you've got the radius. It's all worked out. And you see that, look at this beautiful curve that he has drawn, and it will be hand drawn. And of course, the units used here are different from the units which I have been showing you. But this is from Chandrasekhar's original paper. And everyone should be humbled by the fact that when all this work was done, he was 25 years old. And he did all the work by himself. And of course, he had very great teachers, supervisors, and so forth. But then one of his supervisors, who was Arthur Eddington, he completely refused to believe Chandrasekhar's work, and publicly said that, which was very humiliating for Chandrasekhar. So he left Cambridge and went to the US, and that is where he completed this work. So it's very good history. So now what I want to do is I would like to describe to you this particular diagram, which is very important. But before that, I will stop and ask you whether you have any questions here. And let me see whether any one of you asks a question which will lead to this diagram. Because there's an absolutely obvious question which is staring you right in the face. So let me see if any one of you asks the question. Okay. Any questions? I don't see any hands up. Come on, ask some question at least. Do I see any questions in the chat? No? All right, shall I move ahead then? Okay. Now let me tell you the question which you really should be asking if you are paying any attention at all. And that is, I have constantly talked about T is equal to 0. Okay, but what happens is that you know that the temperature of white dwarfs is not 0. In fact, it is very high, and which is why the white dwarfs are white. Okay, so they have a high temperature of tens of thousands of degrees, and that is why they are white. So the question is, why why is this approximation T is equal to 0, which not only I am applying, but which Chandrasekhar also applied in his work, is it tenable at all? And for that you have to go. To this diagram which I got here. And so you see that this particular diagram, where what happens here is I got the density on the x-axis and I got the temperature on the t-axis. So now, what are the possible equations of state? And in fact, one person asked me this question yesterday, and I said that I'll answer it tomorrow, but the question was not repeated. You see that we have got an ideal gas equation of state, and then we have got we have got the polytropic equation of state. Now there is one very important fact that you must know. You see that there are the protons and there are the neutrons. And there are protons and neutrons in a star, and then there are the electrons. The electrons have a mass which is about 1800 times less than the mass of the nucleons. And so therefore, the electrons become degenerate, but the protons do not become degenerate. Okay, they still remain non-degenerate. So in a certain sense, there are two gases there. One is the degenerate electron gas, and the other was the non-degenerate gas of nucleons. That is one fact that you must remember. Secondly, we have assumed that T is equal to 0. But what happens if the T is not equal to 0? Because I know that it is 8,000 Kelvin and so on. So then you have to use not the very approximate relationship that we used, which led to P goes as rho to the 5 by 3, but we have to use what is known as partial degeneracy. Okay, so let me try to go back to that one and show you. Yes, so you see that this is a fully degenerate gas, but when there is partial degeneracy, then you get the Fermi Dirac distribution where Fp dp dv is equal to this particular factor that you have got here into this factor, and this factor comes from the Fermi Dirac distribution, and T is equal to 0 corresponds. You see, when T is equal to 0, this becomes infinitely large and so forth. And so what we are doing is a particular approximation. So now when I come to this distribution here, you see that a gas can be fully degenerate, it can be partially degenerate, there can be an ideal gas component to it. Now the question is, I told you that when the temperature becomes large, then you get a classical gas, right? So when the temperature is large, so you see that you have got the 10 to the 5 Kelvin, and the density is small, then you see that you get the Maxwell-Boltzmann distribution, and which corresponds to the pressure density relation P is equal to rho kT. Then when at a given point you keep decreasing the temperature or you increase the density, then we go to the quantum domain. So then there are two domains there. In this particular domain, you see that you've got the green line. So this is the line, P goes as rho to the 5 by 3. And why is it a straight line? That is because it's a log plot. And then you have got here, here is a point where it becomes relativistic. So the idea is that if you, at a given density, if the temperature becomes very high, then is the pressure due to the radiation which dominates. When the pressure becomes low, as the temperature decreases, it is the ideal gas state, ideal gas equation which will dominate. But as the temperature decreases, when the electrons become degenerate, so you see that here in this region, bound by this triangle, you got what is known as non-relativistic degeneracy. And then here you have got relativistic degeneracy. And here you have got crystals. What do you mean by crystallization? Is that As the temperature becomes really low, then the electrons and the nuclei combine together, and then you get the usual atomic effects, which will lead to the formation of a solid, for example. Okay, so that is the thing where you get crystallization. So now you remember that we said that the density of a white dwarf is like 10 raised to 6 grams per centimeter cube. Then you see that here you have the non-relativistic distribution. So therefore, what the diagram tells you that the approximation where t is equal. Sorry, one moment. There's a problem with my internet. Can you hear me, please?
Yes, sir. We can hear you.
Okay. So if there's an internet problem, just please let me know. Because my internet connection jumps from this fiber optic one to a Reliance one by itself sometimes.
Sure, sir. Sure.
Yeah. Okay. Thank you. Right. So therefore, the approximation t is equal to 0, where this curve is drawn, is a pretty good approximation. All right. Now I go to the second part of my talk. So what we have done here is I have explained to you how white dwarfs, what are white dwarfs. We've seen how they were discovered. We know that there are thousands of white dwarfs known now. We know that they are degenerate objects and they are very compact objects. We know that there is a maximum mass limit. So now let us go and investigate white dwarfs further, because they turn out to be extremely interesting objects in many different ways. So I will consider just two things. One is that how white dwarfs cool, about which again I was asked a question yesterday, number one. And number two is that how white dwarfs are connected to supernovae type 1A. So what is the picture of the white dwarf we have? A radius of about 6,000 kilometers. And this particular thing here, and there's a star, and it is fully degenerate. But as you go outwards, when you go outwards, in the outermost layer, which is about 50 kilometers thick, then the matter becomes non-degenerate. So you've got a normal gas. So you remember that you've got a degenerate object which is surrounded by a blanket of normal gas. Right? So now we want to talk about white dwarf cooling. So now if you look at a star on the main sequence, like the sun, it is not cooling. It remains, it has got a very perfect, it has got a very steady temperature structure. So outside the temperature is about 6,000 Kelvin for the sun, and inside it goes up to 15 million Kelvin. So you have got a temperature gradient which allows radiation to flow from the inside to the outside. Right. So now there is energy which is being constantly generated inside, and that is equal to about 4 into 10 to the 33 Earths per second. And because of the temperature gradient, this energy is being transported to the outside, comes to the surface, and it is radiated into space from there. And just like you have got very perfect hydrostatic equilibrium, similarly you have got you also have it is not really thermal equilibrium. If it was thermal equilibrium, there will be no net radiation from it. But it is that the amount of energy which is produced inside is exactly equal to the amount of energy which is radiated away. If the energy produced inside were more, then the temperature inside would keep going up, and the rate of nuclear reactions would keep going up, and then they would become uncontrolled and the object will explode. Whereas if you reduce the rate at which energy is produced, then that object could collapses, as we have seen, and then you get a white dwarf. Now, once you have got a white dwarf, the situation is quite different. Because first of all, there is no nuclear fusion. Because all the fusion which can take place has already been finished. So there is stored energy. Where does the stored energy come from? It comes from the fact that when you get a collapse, then you are releasing gravitational energy, minus gm squared by r. And that is the gravitational energy. So the plus part of it is released, gm squared by r, and that heats up the object. And so it is now, so you've got a hot object like this. You've got a hot object sitting here, and which will radiate. Now we have seen that the radiation in a star is because of the transfer of heat in a star is because of radiation and also because of convection. I'm sure you have learned about it in the course. But a white dwarf is different. A white dwarf, the interior of the white dwarf is a degenerate object. So what does it mean by that? Is that the electrons are floating around in the degenerate. But now, you see, now suppose you try to stop an electron in its path. When you stop an electron, what will happen? Suppose there is a collision and the electron loses energy. Then what would happen is that its momentum would decrease. As the momentum decreases, it has to go lower down in phase space. But you remember that this is a fully degenerate object. And even if it is partially degenerate, there are very few lower momentum states available. As a result of which, an electron really cannot lose its energy. Now, these are all strange concepts, but I'm just introducing them to you. But they can all be developed very rigorously. So therefore, the electron has got a very long mean free path. Whereas within the sun, the density of matter is so high that a given electron cannot travel very far. In fact, in the interior of the sun, even a photon has got a mean free path which is just centimeters. But in spite of that, photons diffuse outwards, transferring energy. But because the electrons have got a very mean free path, then they just go all over the place. And it turns out that the energy transfer is very, very efficient. And because of that, the entire object, the entire degenerate part of the object is at more or less the same temperature. So in effect, what do you have? You've got an ideal black body. So you've got a body which is at the same high temperature and it must be radiating. And where does it radiate? It radiates on the surface. So you've got an object at a very high temperature and the temperature changes very, very slowly inside, so we can take it to be practically constant. But here the temperature falls quite rapidly because it is just a normal gas, it's no longer degenerate, and the radiation occurs from the top, from the surface. Okay, so now let us look at some quantitative statements. What is the thermal energy of the white dwarf? I told you that it is proportional to Gm squared by R. But there's an important concept called the virial theorem, which could have been introduced to you. And from the virial theorem, you know that the thermal energy is equal to half Gm squared by R. Okay, where is the other energy gone? That energy has already been radiated away. But you know what is the expression for thermal energy, which is equal to 3 by 2 nkt, where n is the total number of particles. And why is the n coming here? That is because you know that from the thermodynamics that the energy per particle with 3 degrees of freedom is equal to just the principle of equipartition of energy is equal to 3 by 2 kt. So 3 by 2 kt into n is the total thermal energy. And what is n? We have seen that it is the mass of the particle upon the average particle mass. Now, we have always been just taking MP, but we can do a little bit better than that. So what is the simplest kind of white dwarf that you can have? It's a helium white dwarf. This comes from low mass stars. So you take a hydrogen gas and convert the hydrogen to helium in the center, and you go on doing that until all the hydrogen is exhausted, most of it is exhausted, and then you are left with a helium star which collapses to form a helium white dwarf. So let us suppose that we have got a helium white dwarf like that, and it is at high temperature, and therefore it is completely ionized. So then you have got 4 nucleons. So you have got the nucleus of the helium atom, which has got a mass of 4 times mp. You have got exactly 4 times mp because neutrons are a little bit heavier than protons, but we can ignore that. So there, one kind of particle has got a mass of 4 times mp. Okay, then you have got 2 electrons per atom. So then how do we get the number of electrons? The number of electrons is equal to the number of protons. So when you take all that into account, then you see that you have got n is equal to m upon the 3 by 2 factor is 1 upon mp half plus 1 by 4 kT. I would like you to sit down and derive this. It's very, very easy. And which corresponds to the, 9 mkt by 8 mp. Okay, and 9 kT, and this goes as m to the, where did I get this from? 4 by 3, because R goes m here. That is because the temperature, I've forgotten where this comes from. The temperature. Okay, we'll come back to it. So when m is approximately, m is half a solar mass, which is for the average kind of white dwarf. So if you plug in these numbers, okay, then you will get kT. Okay, it is approximately equal to 70 keV. So which means that the temperature is 8 into 10 to the 8 Kelvin. Okay, so if you take an average kind of white dwarf, okay, then you will find that the temperature of the white dwarf is roughly equal to 800 million Kelvin. Okay, so but what you are seeing outside is the temperature of the outer layer. All right. So now, so you see that you have got this object which is radiating at that temperature, and then as it radiates, there is no energy being produced, so the object must cool. Right? So what? Therefore, we want to develop a theory of cooling. So you start with this: make a white dwarf, have a planetary nebula, the matter goes away. You've got the interiors collapsed, you formed a white dwarf. It will be at a very high temperature, but then we want to see as it radiates, it cools. How much time does it take to cool? Does it take 1,000 years? Does it take 1,000,000 years? Does it take 1,000,000,000 years? Okay. So we assume that it radiates like a black body. Okay, and then now the outer non-degenerate layer of the matter, it acts like a blanket, so which sort of constrains the radiation. But that can be neglected for the moment, and in which case we'll get an upper limit to the cooling. So then what is the theory for cooling now? You know that the black body at a temperature T, it has got a radius of, it has got radius, this is a white dwarf radius. So coming back to the Stefan Boltzmann law, the luminosity is equal to 4 pi r squared sigma T to the 4. And this is the amount of energy emitted per second. So which will be the rate at which it is losing the thermal energy, okay, d thermal, and so it is equal to this particular expression here, because this is the expression which is derived. So now you see that here you've got dt, and you've got no other dt, and you've got dt here. There's a t to the 4 here. So if I equate this equation to this equation, it can be integrated very, very easily, and you get an expression for the time. So how is the constant fixed? This is the expression of time. You say at t is equal to 0, the temperature when the white dwarf is formed is very large. You take it to be infinitely large. Then at any given time t, after the formation of the white dwarf, so this is the temperature which is present. So if I know that a white dwarf has a certain temperature, then I can say how long, what is the age of the white dwarf. Whereas if I know the age of the white dwarf, I can say what is the temperature. And so for a half solar mass white dwarf, you see that the age is 3 into 10 to the 9 years into 10, t upon 10 to the 3, and the temperature is equal to t upon 3 into 10 to the 9 years raised to minus 1 by 3. So if you actually look at a white dwarf, the coolest white dwarfs have got a temperature of about 3,000 Kelvin. So if I just take it to be, if I just take it, t is equal to 10 to the 3 for the approximation, then those white dwarfs are 3 billion years old. So what does this tell you? Is that the cooling time for white dwarfs is very, very long. Because please remember that this is an upper limit. This is the upper limit at which the radiation is emitted. Because you are not taken into account the slowing down of the radiation because of the blanket. Okay, when we do all that, and then the detailed models show that over 10 to the 10 years, white dwarfs cannot cool below 3,000 to 4,000 Kelvin. And what is 10 to the 10 years? 10 to the 10 years is the age of the universe. Right? So you see that when you make a white dwarf, it is going to cool slowly. As the temperature decreases, the cooling time increases. And the coolest white dwarf which you are ever going to see It's going to have a temperature of just 3 to 4,000 Kelvin. Okay, and in fact, the coolest white dwarf, which is now known, has about 3,500 Kelvin. So now, what is the use of this theory? This theory is very elegant. What I've done here is just a very, very superficial explanation of it. But the theory has been developed very greatly. And by looking at the distribution of white dwarf temperatures, you get the distribution of white dwarf ages. And that tells you about the star formation history. Meaning that if in a given cluster, for example, if all the white dwarfs are hot, then you know that they were formed recently. But if in that cluster of stars, the white dwarfs are all on the cooler side, then you know that the star formation which led to the development of the white dwarfs occurred very, very long ago. So white dwarfs, the cooling theory of white dwarfs and the observational consequences of it allow you to study the star formation history of objects. Okay, now I come to the last part of my talk. Okay, what do I see here? Yeah. The last part of my talk, which is on supernovae. So I'm sure supernovae have been done here. And I'm only going to, I need only one kind of supernova, which is supernova type 1a. Now, when you know that a supernova, the Crab Nebula is a supernova remnant, you know a supernova occurs when a very massive star collapses. Right? The whole star does not collapse. The outer parts are thrown away. It's the inner part which collapses. And when the collapsing part exceeds the Chandrasekhar limit, okay, then it will collapse to a neutron star. We know that, or a black hole. So a tremendous amount of energy is released. Now, the supernovae which come from this kind of a collapse of the interior of a star are known as core collapse supernovae. But today we are going to consider another kind of supernova, which happen because of a nuclear conflagration. Okay, which means that because of very, very rapid nuclear processes, the whole star explodes and it does not leave behind any. It does not leave behind any remnant. So now, when you look at the supernovae observationally, it turns out that there are two kinds of supernovae. So you look at the spectrum of the supernova. Okay, and then you find in the early part of the supernova, so you are seeing what happened there rather than any synthesis which has taken place. Then you look for lines, absorption lines corresponding to hydrogen. And if these lines are present, then it is called a supernova type 2. And if these are not present, then it is called supernova type 1. So if I look at a spectrum of a supernova and I find that it has no hydrogen features, and then until 1985 I just called it supernova type 1. But now I know that in addition to the supernova 1, no hydrogen features, it has got specific features corresponding to heavier elements, and then the silicon features dominate. So I look at a supernova. Is there hydrogen present? Yes. Then I know it's supernova type 2. If there's no hydrogen present, I further ask a question. Are silicons present? If it is yes, then it is supernova type 1a. And if there is no feature present, then if there are only helium features, then it is supernova type 1b or 1c. I'm not going to go into these now. Right? So the classification of supernova type 1a is based on spectroscopic features. Okay, and now what is the amazing thing is that you study lots and lots and lots of supernova type 1a, and you find that they have very similar spectroscopic properties. They have very similar light curve shapes, and the absolute magnitude and maximum is remarkably homogeneous. So what do I mean by that? Look at this here. This is a particular supernova, and then you have got the magnitude which is changing. So, so you see that now you know that the magnitude of the inverted scale, and therefore as the magnitude decreases, the brightness increases. This is a point somewhere here the supernova is born, and then it becomes brighter and brighter and brighter quickly. Okay, and then it reaches a maximum. Okay, and then the thing goes on. Now, what you can do is you can ask what is the brightness of the supernova at the maximum. And then you study 100 supernovae type 1a. And you get the remarkable fact that the absolute magnitude of the supernova, either in the B band or the V band, is approximately equal to minus 19.3. And this is the measurement error. There also, it is not absolutely the same. There's a dispersion around it, and which is less than 0.3 magnitudes. So this is a remarkable fact. But the supernova, you see that if supernova type 2, for example, can come from an object which is 30 solar masses, 20 solar masses, 80 solar masses, or whatever. So therefore, their brightness cannot be the same. But in this particular case, in the case of supernova type 1a, it turns out that the brightness at the maximum is the same, always. If you actually study a large number, you find because of this dispersion, some are brighter or fainter. But then there are ways in which it can be scaled, and you can show that the curve is indeed, apart from the scaling, it is terrifically homogeneous. And what does that tell you? It tells you that if there are, it means that the progenitor, must be pretty unique. It can't be one kind of star once, one kind of star another, and the progenitor will be unique. And then with a fair amount of thinking, calculations, and simulations, it became clear that a very good progenitor would be an object which is just at the Chandrasekhar limit. So imagine that you've got a white dwarf, which is at the Chandrasekhar limit, and then its mass increases just slightly. Then what will happen is that it collapses because then the Chandrasekhar limit is violated. And when it collapses, if you look at the details of the collapse, you find that it is not going to lead to the formation of a neutron star. It is going to exceedingly fast nuclear reactions take place. And so the whole thing bursts out. And when it bursts out, because it is always an object of the mass close to the Chandrasekhar mass, it means that the amount of energy which is released into the supernova which takes place, there is no compact object which is formed, must be nearly the constant. So this all seems very hunky-dory. The problem is that you have very, very few white dwarfs close to the Chandrasekhar limit. Okay? Because most white dwarfs, 85% of white dwarfs have 0.8 solar masses. Okay? So then, where will this kind of an object accrete matter? How can it do that? And so that it goes close to the Chandrasekhar limit. One way of that would be a binary system. Right? Because you know that in the binary system, a compact object can attract matter from the companion. I'm sure that Dipankar, Bhattacharya and others have talked to you about it at length. And I myself considered the processes briefly when I talked about black holes. Right? So you see how beautiful the argument is that the supernova type 1a are very homogeneous in their properties, and therefore the underlying progenitor system must be very homogeneous. And it stands to reason that it's a white dwarf close to the Chandrasekhar limit which collapses. And then, but we can't have such white dwarfs which are single, and therefore you put it in a binary system. So when you've got white dwarfs, and it is not that such objects are known, we know hundreds of white dwarfs which are in binary systems. And it turns out, I've got just a couple of minutes left. It turns out that such objects, there can be two kinds of white dwarf binaries. One kind is called a single degenerate model. What does it mean? Is that a binary always have two objects in it. Now it turns out that one of them is a white dwarf, with typically a low mass carbon oxygen white dwarf, and then the other is a star, which is typically a low mass. Okay, so then now what can happen is that there can be accretion of matter from the other star to the white dwarf. It goes on accreting matter, and then it exceeds the Chandrasekhar limit and it explodes. So look at this beautiful picture here. This is not a real picture, of course. Is that you've got a white dwarf, and then this is a star which is filling the Roche lobe. I've already mentioned Roche lobes to you. And matter passes through the first Lagrangian point, it carries angular momentum, and therefore it forms a disk, and then it just and the disk, and then the disk quickly collapses onto the white dwarf, and you get the supernova type 1a. So you see here, you've got two stars. The primary star is always the more massive. It evolves, forms a red giant, explodes, and forms a white dwarf. And then you've got the main sequence star, which in its own sweet time develops into a red giant and then pours matter into the white dwarf. Its mass reaches the Chandrasekhar limit. It explodes into supernova type 1a. Right? So, a very nice story. Then, then there's another quite different model possible, where it's a double degenerate model, meaning that both the objects in the binary are white dwarfs. And is this a figment of the imagination? It is not. We know any number of binaries in which both objects are white dwarfs and both objects are neutron stars, and all the LIGO observations have talked about binaries in which both objects are black holes. So this is not a very exotic object. Now the point is that you could have a binary with two white dwarfs, and because of the evolution, these binaries, these white dwarfs were fairly close to each other. So you've got two very compact objects, just a few thousand kilometers in radius, several thousand kilometers in radius, which are going around each other, and they are massive, and therefore they must be emitting gravitational waves. Okay, then what happens is that when they're emitting gravitational waves, they lose energy, and therefore the object keeps shrinking. Because you see that minus gm squared by r, as that becomes more negative, obviously r decreases. Right? So therefore the object keeps shrinking. Then the less massive white dwarf, you know that the lesser the mass, the greater is the radius. So the less massive white dwarf, it fills its Roche, quickly forms a disk around the companion, okay, and then the two merge into each other. Okay, the two just merge into each other. And when they merge into each other, you will get a catastrophic explosion, which is supernova type 1a. Now it turns out that there are problems. Such thing will definitely happen. The frequency with which the gravitational waves are emitted by objects like this is such that the current LIGO detectors cannot detect them. And so we'll have to wait until we got space mode detectors, which could go to much larger wavelengths and lower frequencies. Okay, so that is what you would get. That's where we'll be able to actually detecting gravitating white dwarf binaries. So you see how white dwarfs are at the progenitors of supernova type 1a. And I'm sure that you have learned by now that supernova type 1a are very important in cosmology because of the uniform luminosity, they're able to provide a standard candle. And then the people who worked on this standard candle and therefore were able to show that the universe is accelerating, so they got a Nobel Prize for that. Right? So thank you very much. I'm done.
Sir, are you going to take a question? Because I can see the two people has raised that.
Yes, I'll be very happy with taking questions. No problem.
Okay. So I'm just unmuting Sachin Dubey.
Yeah.
Am I audible, sir?
Yes, you are.
So when you discussed about the white dwarfs, and you stated that over the 10⁻10 years, the white dwarf will have at least like final temperature will be between 3000 to 4000 Kelvin, right?
Yes.
So that much it can cool. So the reason why it couldn't go below that?
There's no time. There's no time. You see, because I told you that 10 to the 10 years is the age of the universe, right?
Yeah.
Yeah. So if you make a white dwarf 10 to the 10 years ago, by now it would have gone to 3500, but it has not. So if our universe is infinitely large, okay, then you would have white dwarfs which have been cooling for a very long time and will be much cooler. But you wouldn't be able to see them, right? Because you know that as you go to about 10 to the 10 years, you hit a wall in the sense that you are looking at the Big Bang at that point. Right? So our horizon is limited to about 10 to the 10 megaparsec. And therefore, you will never be able to see white dwarfs which are cooler than a few thousand Kelvin.
So, okay.
Yeah. Other questions?
Yeah.
Sir, I actually was asking for if you could please provide some study materials on this study of white dwarfs.
Provide what?
If you could please provide some study materials on this on the study of white dwarfs.
Okay, what I will do, see, there are two things I can do. One is easy to do. I just put out some textbook material or any other thing that I have, some papers which I use. I'll do that. I'll pass it to Dipankar Banerjee and people, and who will pass them to me. Number one. Number two is that both in terms of the mass, that I talked about black holes across the mass spectrum, and then I've talked about white dwarfs. These are both new talks, meaning that I had not given talks in this kind of configuration before. And then I just scratched the surface. So if some of you, 10 people, 20 people, are seriously interested in learning more about these objects, so you could inform me through the organizers, and I'll be perfectly happy. I will tell IUCAA to organize further lectures for you on that, which I'll be very happy to give. And I could even bring in a couple of people who are more expert than I am. Right? So this applies both to black holes as well, the two topics that I covered, black holes and white dwarfs. Right? But that I will do that only if there are people who are seriously interested.
Definitely, sir. Definitely, I'll do that. Definitely.
Okay, but then I'll let you have this book.
Okay, thanks. That would be great, sir. Thank you. Thank you, sir. Thanks a lot.
Okay, there are some.
So there is one more question from the Neil.
Yeah. Who is that?
Hello, sir.
Yeah.
My question is that when we see a type 1A supernova, it has a strong emission lines in silicon. But
Yes.
white dwarf is generally carbon, nitrogen, oxygen. So how does this silicon appear?
Okay. So you see, what happens is that you are not really seeing the spectrum of the silicon at the time. You are looking at the spectrum of the supernova. Now you know that supernova is the ambience of the supernova is extremely hot. And so therefore there's a lot of nucleosynthesis which takes place. And it is that which gives rise to these heavy elements. So it's all happening in the supernova.
Okay, sir.
It is all coming from the white dwarf.
Okay, sir.
Now I can read a question here in the chat box which is, how was the Chandrasekhar limit experimentally verified? I mean, you know that these kind of very direct questions. Tell me how you know that it is correct. The theory is very elegant, but how do you know it is correct? That I mean, these are the kind of questions that you should be aiming for. Okay, this is by Raunak Tolani. You see, what happens is that people have never found a white dwarf which exceeds the Chandrasekhar mass. Number one. Number two, when you actually measure the masses of neutron stars, it's quite difficult to measure the masses of neutron stars because there are certain uncertainties because of the you don't know the inclination of the orbit of the binaries. You can only measure mass with the binaries. Now it turns out, and I'm sure you have heard of it before, is that there is a neutron star binary. Okay, meaning that the object will consist of two neutron stars which are going around each other, and the object is very compact. So general relativistic effects dominate, are present. As a result of which you can exactly measure the masses of the neutron stars. And then they are amazingly close to the Chandrasekhar limit. So now we have measured lots and lots and lots of neutron star masses, and they are all very close to the Chandrasekhar limit. And there are a few small exceptions here and there which are. So therefore, nature does respect the Chandrasekhar limit. Now the other question which says here by Ayush Gar, okay, it says that why shouldn't because the matter is very hot, shouldn't it be relativistic? It's very simple. I mean, you take matter at a temperature of 10 to the 6, 10 to the 5, 10 to the 8, and you just see at what point it becomes relativistic. Okay, so you will find that it really does not become the matter inside. So the temperature in the sun is 15 million Kelvin, which is 1.5 to 10 to the 7, and you will find that it is not relativistic at all. You get relativistic matter in a white dwarf because of the Pauli exclusion principle. the lower levels are all occupied, and so the electrons are forced to get to the higher levels, and that is why you get it. So that is why you get a relativistic case. What constraints? This is a question by Muhammad Raibul Islam. I said, what constraints determine the outer thin layer of the non-degenerate gas? So as I told you, the calculations which I have presented are very hand-waving kind of calculations. And you can sit down and do the whole thing in detail. And some of the textbooks which I will recommend to you, they'll have these calculations, how you get the thin layer and so on. Okay. And then the same person has asked, so does that mean series B will end up in a supernova 1A? I suppose so. And so it depends, because it is not a closed system. It won't be. Because Sirius and the white dwarf, they are not sufficiently close. I don't know how much Sirius will expand, but this is a very interesting question. It will depend upon the details of the system. We'll have to work that out. Yeah, I already answered this question, but Ananya Biswas about how do we get the silicon lines. Okay, so that's the end of the questions. So that's fine. All right, then, thank you very much. I'll end my talk.
Thank you, sir.
Thank you.